Use the long division algorithm to write the decimal in fraction form. Okay, so we're dividing 9 by 16. 16 does not fit into 9, so we put a 0 on the top. And after the 9, there's an invisible decimal. Now we look at 90. So let's see, how many 16s can fit into 90? Well, that'd be 16, 32, 48, 64, 80. So we're going to put 5 of them, which gives us 80. Then subtract. 90 minus 80 is 10. Bring down a 0. So we were at 5 for 80. And if we add another one, that would put us at 96. 100 minus 96 is 4. 16 times 2 is 32. 40 minus 32 is 8. Bring down another 0. And 16 fits exactly into 80 5 times. So this one is 0.5625. Please divide 5 by 8 and 6 by 25 to find the decimal version of those two fractions. Is this decimal a rational number or an irrational number? And explain. Let's go back and think about some definitions of those two phrases. So here are some quick definitions that might help us determine whether this is a rational number or an irrational number. I would suggest writing these definitions in your composition book under your warm-up from this morning. So a rational number can be written as a fraction with whole numbers on the top or bottom. So like 5/7 is a rational number because the top and the bottom are both whole numbers. You could also think of -1/9 as a rational number because those are both integers on the top and bottom. It can also be written as a decimal with a repeating pattern. So for example, 0.68888. The 8s are repeating. The piece where it says or terminating would be like 0.25. And terminating has a pattern that repeats also. It just repeats a bunch of zeros. But we don't write those because they're not necessary. So terminating means that it stops or that it repeats zeros. But irrational numbers have an endless, non-repeating set of digits that show up after the decimal point. So in this specific example, we have 21211, 2111. And so even though there's a pattern there, it's not repeating. Repeating would be like 21, 21, 21, 21. And so this is considered an irrational number. It does have a pattern, but it's not a repeating pattern. Again, I would include those notes in red in your composition book for later reference. Consider this rational number, 308 over 101. Find the decimal form. All right, so 101 can fit into 308. 3 times. That would give us 303. 308 minus 303 is 5. Bring down a 0. 101 did not fit into 50. So we're going to put a 0 here. 101 will fit into 500 4 times. 500 minus 404 will give us 96 left over. 101 fits into 906 9 times. That would leave us with 51. 101 will fit into 510 5 times. That leaves us with 5. But 101 does not fit into 50. And it does fit into 500. You'll notice here that the 50 as a remainder showed up again. So now we're going to have 4, 9, 5, 0, and it's going to continue to repeat from here. So the way that we would write that is 3.0495, and the chunk that repeats is from the 0 to the 5. So we're putting a line over this section. We don't need to continue writing out repetitions. We just put a line over the chunk that repeats. Then it says, why do the digits form a repeating pattern? Well, the remainder in the division repeats in the same order as well. So if we continue to write the 4 down, we would again get 96, which showed up there. So the remainders repeat in the same order. For problems 3 through 5, write the fraction form of the decimal. So I'm going to also write notes for this type of problem, just so you have them as a reference as well. Again, I encourage you to add those to wherever you keep your notes. In my class, that's in your composition book. So to start, we're going to set x equal to the decimal we are looking for. Then we are going to multiply until we get one set of the repeating decimal outside of the decimal place. So the way I that was multiply by powers of 10 to move one repeating chunk out of the decimal and into the whole numbers. So in this case, there's only one number that repeats. So to move the decimal to get that out of the decimals and into the whole numbers, we would multiply by 10 on both sides. Now that's going to move this decimal here, but it's repeating. So for example, it's 0.444444, and it continues on forever. So when I multiply by 10, it moves this decimal to this location, which would be 4, with a bunch of 4s after it that are repeating. If instead you had something like 47 repeating, we would multiply by 100 to move the decimal 2 spots, which you'll see in future lessons. Okay, then we are going to subtract. So it will look something like this. 10x equals 4.4 repeating, and we are subtracting x, and we are subtracting 0.4 repeating. So we're subtracting this whole equation. So when I subtract, I have 10x minus x is 9x, 4.4 repeating minus 0.4 repeating. The repeating 4's are eliminated, and 4 minus 0 is 4. So in the next step, we will solve for x. So we will divide both sides by 9, and x equals 4/9. Now, a lot of times my students are tempted to type in 4 divided by 9 in your calculator, but when you do that, it's just going to give you the same thing that you started with. The whole goal was to change it from the decimal to the fraction form, so we want to leave it like this. So here in number 4, again, set x equal to this. Then we're going to multiply to move that decimal piece that repeats into the whole number. So that's going to need to move one spot. So we just multiply by 10x, and that would give us 1.1 repeating. Now we will subtract. x minus x is 9x. 1.1 repeating minus 0.1 repeating is 1. Divide both sides by 9, and we get x equals 1/9. Again, we don't want to change it back to a decimal. We're writing them as fractions. So this is x. We want to move that decimal to the end of the repeating chunk. So that's going to take moving it once, so just 10. And now it's 7.7 repeating. 7.7 repeating minus 0.7 repeating is 7. And x minus x is 9x. Then divide both sides by 9. And x equals 7/9. Make sure you have your notes written down for multiple parts of this lesson, as well as your workbook filled in with those to reference, because we're going to use those types of problems again tomorrow.